and the motivation of our research and a brief review of our models. After making the spectrum of particle clear, I will analyze the scalar potential and its three-level stability, as well as the detail of scalar sectors such as charge scalar, CPO, CP even, and complex scalar. From the Yukawa interaction, I will help you to take a look on radiative inverse seesaw mechanisms to generate the neutrino masses. I will also talk about the resonant leptogenesis of our model in comparison with 3 sigma rank of baryon asymmetry of universe. Lastly, I will talk about the electron anomalous magnetic moment in our model. And after all, I will make some conclusion about our model. And here is my research group. My supervisor, Professor Hoàng Ngọc Long. He's now working at Văn Lang University in Ho Chi Minh City in Vietnam. And he collaborates with Professor Antonio for more than a decade. And Antonio is now working at Técnica Federico Santa Maria University in Chile. Am I say right? Design. My collaborator as Associate Professor Đỗ Thị Hương. She working with me in the same office, and yes, is a PhD student Phạm Ngọc Thư, and here's me. I am Hoa Binh. And with Professor Antonio, we collaborate with Dr. Cesar Bonilla and Dr. Vinudas, who working in Técnica Federico Santa Maria University. And one more person I want to mention here is Professor Ivan Smith, but now he has gone away. But I really want to mention him here because we work with him about on this manuscript. And now I will tell to you about our motivation, because our research motivation are raised from a few limitations of the standard model along the progresses of the high energy experiment. In standard model, neutrino are massless, and there isn't a neutrino mass generation mechanism, while experiments show that there are neutrino oscillation, which means neutrino are massive. Also, standard model cannot explain neither the observed dark matter relate abundance nor the antimatter asymmetry of the universe. Moreover, the standard model doesn't have the answer to the question why there are 3 generations of fermions, or the electric charge quantization, or the observed hierarchy among the masses of charged fermions, and so on. So the challenge requires the extending of standard model by extending the electroweak Gauss symmetry from SU2 left times U1 Y to SU3 left times U1 H or SU5 or SU2 left times SU2 right, and etc. So another way to extend the standard model can be adding some new particles such as a scalar field or isotic fermion. One another way to extend the standard model is combining the standard Gauss symmetry with adding some new particle, so that we have a duration of high energy physics, which is called beyond standard model. So why we choose the 3-1 models? Because we have some property, I will tell to you some property of 3-1 model, which is based on SU3C times SU3 left and U1 white, U1 Gauss symmetry. First of all, this model can explain the number of standard model fermion family and explain the quantization of electric charge, and they can provide the additional source of CP violation as well as a natural Patrick symmetry. We can all use this model to predict an upper bounds of the weight missing angle theta 1 bet, and this model can include the potential candidate for cool dark matter, such as SQUIM or axion and etc. But because we use seesaw mechanism, we can explain the tiny masses of neutrino, and so that we choose the 3-to-1 model and we impose some discrete symmetry and introduce some new particle. Is our particle here. I will turn to you. In this paper, we introduce two models based on SU3C, SU3Lab, and U1H. But I think I will focus on a 3-to-1 model with one loop level of inverse seesaw at radiative scale. Because I think it's just the difference from the scalar field and the isotopic quark and lepton, but the phenomena that we analyze get the same result. So I will just focus on just one loop model. And let's say now we will take a look on the spectrum of the model. We introduce here we introduce 6 scalar fields with 3 triplets and 3 singlets as in the equation 4, and take pay attention here that we just only 3 triplet rho, eta, and chi with a vacuum expected value just belong to the neutral scalar field with a different quantum number. And 3 singlet bar phi, zeta, and sigma is a complex scalar with a VV, and zeta is a real scalar with non-zero VV. And the last one, the sigma, is a complex scalar with non-zero VV, which will help us to predict the dark matter candidate in the model. This scalar also helps us to give mass to all of the particles in the model, but from the equation 5, you can, here we present all of the left-handed fermions of the model. The first generation of the quark are in the triplets with J1 and an isotopic quark, while 2 other generations of quark are in the anti-triplets with Jn, also isotopic quark. All of the left-handed leptons are in triplets, and remind that all of the right-handed fermions are in singlets. You can see here, singlet with under the SU3 lab. Here it is. And so let's say the fermion sector includes the fermion particle of the conventional 3-to-1 model with right-handed neutrino. There are 3 charged vector line lepton I, E, and 2 additional neutral lepton per side, transforming at a singlet under the SU3 lab. This is important for us to define the neutrino mass via one loop level. And so with this spectra of the particle, the model has a scalar potential like this one, like V1 with A here is a mass parameter, and B is the coupling constant of the quadratic interaction of eta, rho, chi, and zeta. Because this quadratic interaction is forbidden at 3 level, then the coupling constant B should be, this one should be tiny. Using this scalar potential, we determine the minimum condition of scalar sector at the phi equation. We can define the mu chi, mu eta, mu rho, mu sigma, and mu zeta. And then we consider the scalar sector in three parts. For charged scalar sector, CPO sector, CP even sector, to find the Goldstone boson of the model, as well as the scalar boson and the pseudo-scalar boson. For charged scalar sector here, in the basis of rho 1 minus and eta 2 minus, we get a massless Goldstone boson Z1 minus and a charged massive Higgs with mass is given in equation 7, and the missing angle is defined by the equation 8, like this one. And similarly, with the basic of rho 3 and chi2 minus, the model has a massless Goldstone boson and a massive charge with physical state as in the equation 9, and the missing angle alpha 2 is the alpha 2 is defined as in equation 11, like this one. So you can see here, as we assume the hierarchy of the vacuum expectation value should be V chi is much lesser than V rho and V eta, so this alpha 2 should be very small. So for the charge scalar sector, we will have two charge Higgs with massive and two Goldstone boson, Z1 and Z2. About the CPO sector, we can recognize that the scalar phi, var5, this var5 doesn't mix with any other, and its mass is given as in the equation 12 is depend on the parameter A in the Higgs potential that I mentioned above. And this is the components of a complex scalar, which is a characteristic property of 3-1 models. In the basics of I chi3, I rho, and I eta 1, we can define two Goldstone boson which corresponding to Z and Z prime boson. They are massless, and thus they only one pseudo-scalar A1 get mass at in the equation 40. And the missing angle we can define, you can see here the rotation matrix is include three missing angle, alpha 1, alpha 2, and alpha 3 is defined by the equation 15. Is also tiny. And moreover, in the basic I chi1 and I eta 3, we can define the Goldstone boson of a longitude component of neutral Gauss boson X is defined as in the equation 16 here. So, and we get another pseudo-scalar massive is A2 with the mass given in the equation 17, with the missing angle is very tiny, as shown in the equation 18. And next we consider the CP even sector, where we recognize that this the real part of phi is doesn't mix with the other, and it gets the same mass with I phi. With the same mass with I phi, and in the basic of sigma and chi3, we define two neutral Higgs that gets that massive with the mass given in the equation 24. You can see here that the main contribution of this mass should be Vk. So it will get mass at TeV scale. And the missing angle is defined by the equation 21. Here you can see this beta 1 should be very small because of the hierarchy of the VV. And in the basis of A zeta, A rho, and A eta 1, we can define another Higgs boson, where this 81 is the small 8, this one, sorry, should be the standard model like Higgs and get the mass and I saw in the equation 25. And this one can be at the electron scale if the product of B and Vk should be at GV scale. Another Higgs boson should be at 3 and at 4. It can get mass as I saw in the equation 26, and the missing angle is defined by the equation 27. This one is significant because we V and V zeta are both at electron scale. I mean that this 3 and 4 are significant missing. And so both of why I mentioned here, because both of these why it's important to analyze the scalar structure, because this beta 1 and beta 2 and beta 3 help us to do numerical analysis for G-2 and leptogenesis in this model. So take a note for beta 2 and beta 3 because it's significant. And the scalar potential help us to determine the masses of scalar, and in the model, the Yukawa interaction will help us to give mass to all of the fermions in the model. And with research, we focus on neutrino masses, so that I just consider the Yukawa interaction of lepton, and I show it here. Here is the Yukawa interaction of lepton. From this one, we find out the mass term of neutrino, as I saw in the equation 28. And here you can see the mu is the 9 times 9 mass matrix. And let's say this m psi is mass of additional neutral lepton, which is given by the equation 29. And mu here is include some parameter that's small m. This one is defined by 0 and x0 left, x0 darker, minus x0 left star conjugate. And so in the equation 30, this capital M is the mass of right-hand Majorana neutrino, and mu here is a mass parameter that's generated by one loop diagram and is defined by one loop integral in the equation 32, where has the contribution of neutral singlet lepton by this one, and the scalar singlet var phi here. So here is the diagram of one loop Feynman contributing to the Majorana neutrino mass submatrix M mu in this model. Let's say we can discuss something about it, because if we assuming that the submatrix satisfy the hierarchy, that mu is much smaller than this mu, than this M, and this M should be smaller than the mass of Majorana neutrino. So we can see that the smallness of the neutrino masses is regulated by the linear dependence of the parameter mu. If mu come to zero, this mu come to zero, then mass of neutrino are zero, implying the lepton number conservation. One can argue that mu has a radiative origin and the submatrix M and the capital M arise at tree level. This could lead to an explanation of the hierarchy that I mentioned above, and we can explain the small neutrino masses via seesaw mechanism as inverse seesaw mechanism as a radiative scale. After explaining the small neutrino masses, we consider the resonant leptogenesis. Here is the, yes. In physics, we consider the leptogenesis is a generic term for hypothetical physics processes that procedure and asymmetry between leptons and anti-leptons in the early universe, resulting in the presented is a present-day dominance of lepton over anti-lepton. In the currently accepted standard model, lepton number is nearly converse and at temperature below the TV scale, but some process can change this number. At high temperature, it may change through the interaction with let me remember, with barons, particular entity. In both of these cases, the process involved is related to the weak nuclear force and is an example of chiral anomalies. So that you can, in this model, we consider the lightest pair of the heavy pseudo-Dirac neutrino, nu and nu right one, plus to minus. Here is where the, sorry, let me check. No, this one. No, not this one. Okay, here the a minus one, and we can define via the the CP asymmetry is given by this equation. And in this one, this zero left is defined by the mass missing the mass of Majorana neutrino and this mu parameter. This A is defined by this H-rho left and H-rho left plus. And this R is defined from this M1 this M1 minus and M1 plus. So let me check. So the baryon asymmetry parameter in the weak and strong was our regimes. is defined by this eta b, where the effective watt-hour parameter is defined by this gamma, this M1 minus and M1 plus. But here you can see that this the Hubble parameter is defined by the equation 41, and because we can see that the expression for the baryon asymmetry parameter in the weak and strong watt-hour regime are given as in the equation 38 and 39, and so that you can see from the equation that the parameter is of this model influencing the baryon asymmetry and define this let's say this one includes the generation of light active neutrino masses and the non-unitary of the neutrino mass missing matrix and processes involving lepton flavor violation. So here is the numerical analysis we try to present the correlation of baryon asymmetry against the mass of the lightest heavy neutrino. The left figure here is the presentation of the parameter space with watt out, and you can see the blue light here is 3 sigma range of baryon asymmetry universe. The green spot here plot here is the bonds of P and MS matrix, and the gray plot here is the correct active lighted neutrino masses. Here is for the which was our right knee, and here's for the left is on the left, and for the strong watt-hour right knee is on the right side. You can see that the correct active light neutrino masses is very tiny in comparison with watt-hour right knee and strong watt-hour right knee. We try to present the baryon asymmetry parameter as a function of this one, and we can see that is the correct active light neutrino masses is getting smaller, and for weak watt-hour right knee, but for strong watt-hour right knee is approximately disappear. So from the figure, we can see that the parameter space that successfully explains the observed matter and antimatter asymmetry in weak watt-hour right knee correspond to the last value of Yukawa coupling, while the parameter with strong watt-hour here is correspond to the very small Yukawa coupling. Because of this, the weak watt-hour case does not get the constraints by the bonds of the non-unitary PNMS matrix. And the unitary violation is very small in this case. And let's see, you can see here that in the weak watt-hour case here, the correct baryon asymmetry is satisfied to the lightest heavy neutrino with mass. It should be lower than, no, it should be not lower, it should be larger than 1 TeV. And in the strong watt-hour right knee, this satisfies for, let's say, yes, right. It should be certified from this M1 as light as a few hundred GeV. Yes, yes, sir. Okay. And so that we consider about the correlation between the mass of the lighted heavy neutrino or the parameter space in the mu to E gamma decay. And in this picture, in the figure, the colors can represent the value of branching from mu to E gamma decays for the corresponding point. This one. Let's see. Oh, the figure in the left and right here is correspond to the parameter space with which was out and strong was out respectively. But I mean, no, I'm not sure about it. And this figure is the correlation of the baryon symmetry parameter against branching mu to E gamma. The horizon blue lines represent here, as I mentioned above, it should be 3 sigma in range of baryon asymmetry of universe. And this red line, yes, this red line should be correspond to the mu to E gamma bonds on branching of mu to E gamma. And I mean that our numerical analysis on leptogenesis is suitable to explain the metal and antimetal symmetry, but it's just a little bit. And now we turn to talk about the electron anomalous magnetic moment in this model under the condition in this model. The expression of the muon anomalous magnetic moment and electron anomalous magnetic moment take the form at this equation 42, where kappa and gamma is defined as the left and right rotational matrix, which are used to diagonalize the mass missing matrix of lepton. And at one, these are it, the inversion of the rotational matrix of CP-even mass missing matrix. And IS here is the loop function defined by the equation 44 like this one. And pay attention here that this M this here is the mass of isotopic lepton, and E and mu is the mass of electron on muon, and this MS or MP is the mass of scalar field or pseudo scalar field that we define in the scalar sector. By numerical analysis, we present the scatter plot corresponding to the result of our numerical scanning. This one is with this one show the value of delta AE. Why we choose AE? Because this AE in our numerical analysis it should be somewhere 10 to 13, and is smaller than delta a mu. So if we can, we should to present the delta AE. Let's say, so we can see that the mass of the charged acidic lepton E1 is can come from 100 to 20 to 250 GeV, and so that almost the value of delta E should become from 3.5 times 10 to minus 9, and so that of the charged acidic quark lepton E2 and E3 reproduce the observed of delta E mu. In our analysis, we fix this at one, as I define in the CP even sector. The at1 should be get 1 TeV and at2 get 0, let me remember, 0.9 TeV, and various the charged lepton acidic masses between from, no, I think this mass of E1 should become from 100 GeV to 1 type. It should be better, and then we can get the result in the region of 100 to 250. Yes. So that our proposed model capable can accommodate the experiment value of the muon anomalous magnetic moment. For the second model that we introduced in our paper, we consider the two-loop model. The two-loop Feynman diagram contributing to the Majorana neutrino masses at submatrix. We also based on the 331 Gauss symmetry, but we just only impose U1 LG, this global symmetry of lepton. As so in this equation 45, we introduce a scalar field to the model where there are two charged singlets, zeta and this zeta and c, no psi. Zeta and psi, we will have us have more charge h at 3 and at 4 plus to contribute. We can contribute to the loop in this model. The difference of the scalar sector and Gauss symmetry make the difference of the charge U1L charge of the for all fields of the model. But when doing numerical analysis for leptogenesis and electron anomalous magnetic moment, this second model gives the similar result as the model with one loop, so that I skip the two loop model and I just introduce the particle spectrum here. To finish my talk, I want to make some conclusion that the radiative inverse seesaw 331 model with one loop and two loop level are based on 331 model, including the global lepton symmetry, and can generate small neutrino masses via radiative inverse seesaw mechanisms. Also, the masses of standard modern charged lepton arise from a three-level seesaw mechanisms, and the mass spectra of the scalar particle, mass spectra of scalar particles are studied in detail, and there can be 2 CP even particles with mass in range of electroweak scale. And the modern parameter influenced the baryon asymmetry by numerical analysis via leptogenesis, and our proposed model capable of successfully accommodating the experimental value of the muon and electron anomalous magnetic moment. So I finished my talk, and thank you for your attention.
Thank you very much, Binh, for the very comprehensive and nice talk. Question from the audience?
Yes, I do have a question.
Yes.
First, could you go back to the slide 13, if I'm not mistaken?
Yes, here.
Yes, that one. So in this plot, first, could you remind me what X whole stands for? Is this a new color coupling?
Yes, we define from the Yukawa coupling.
Okay.
Yeah.
So in this plot,
I think I remind that this because I remember that this which was algorithm and strong what algorithm is involved to the electroweak box, so that it should come from the Yukawa direction.
Okay. Okay. So this bound from the PMNS matrix, this green region is excluded. Is the region excluded by this constraint, or the region accepted for the constraint?
I think the reason of this the bonds of PMNS gets come from the experiment, the data of experiment that you can see.
Yeah.
Yeah.
No, sure. I just wanted to clarify whether what is the viable region in this plot. So there is this gray region which produces the active light active neutrino masses. Okay, and then there is this green region. So my question is whether this region is excluded by PMNS, or is still viable?
So the green region is viable from non-unitarity of the PMNS. For instance,
Okay.
yeah, once you incorporate the bounds from non-unitarity, then the gray region will be disfavored. Only the green region will be.
Will survive. No, okay, and actually makes sense because the mass of the particles are increasing, so in general you get
for lower masses, higher the unitarity.
From GB to GB.
Okay. Okay, and just another question. Have you considered a dark matter candidate in these models?
Yes, I think the dark matter candidate can be arise from the CPO sector. It can be that I saw here. Maybe it can be I1. It just can be I1 because it's the combination of these 3 components. We can consider about the VAR5. This VAR5 here can be the major role, and it also can be a dark matter candidate. But actually, I think the cool dark matter candidate here can be an axiom-like particle. It can be this I1.
Okay, but in these works you haven't analyzed in any detail the dark matter candidate, no?
Yeah, no, we didn't analysis about the dark matter candidate in this model.
Okay,
Actually, I think it is Yes, I will think about it. I will rethink about it.
Okay, thank you. Thank you, Ben.
No problem.
I would like to add comments regarding this Dharma issue. And is that, for example, in this model 1, I think it will be most, will say, viable to take as a Dharma candidate either the real or imaginary part of the bar phi. We had that this symmetry is broken, but we had a preserved C2, let's call it C2 tilde symmetry, arising from the spontaneous breaking of the U1 lepton number symmetry. When and the C2, the corresponding C2 charge will be -1 to the 6 times L, where L corresponds to the charge of the particle under this global U1 lepton number symmetry. So this will imply, for instance, that the bar phi will transform non-trivially under the preserved C2 tilde symmetry arising from the breaking of the U1 lepton number symmetry. The preserved C2 symmetry guarantee the stability of the dark matter candidate, which could be either real or imaginary part of the bar phi. It will depend on the sign of the trilinear scalar coupling phi square sigma, which is invariant under the symmetry. But if we take this trilinear coupling of the phi square sigma interaction to be positive, then the imaginary part, being was mentioned, the imaginary part of the bar phi will be the lightest particle having non-trivial C2 tilde charge, and therefore it will be a scalar dark matter candidate. On the other hand, we also had fermionic dark matter candidate because we had at the last line of the last table, at the left of the slide, the size, they had U1 lepton number symmetry, U1 lepton number chair assignment as a one half. So the C2 tilde chair will be -1 to the -1 to the 6 times that chair. So we will have non-trivial chair under the preserved C2 symmetry. So in principle, we may also have the fermionic dark matter candidate, which will be the lightest among phi 1r or phi 2r fields. So we had both a scalar and fermionic dark matter candidate, and we had two scenarios in that model for the dark matter candidate. And similar situation may, in similar situation is happened also in the model 2. In the model 2, we had just one preserved C2 symmetry arising, we had a preserved C2 symmetry, C2 tilde symmetry arising from the breaking of the lepton number symmetry, and we don't have the extra cyclic symmetry in the model.
Yes, right.
So this
Because
for clarifying the dark matter issue.
you mean that because we didn't impose the Z2 symmetry, so that maybe we can get sigma or phi over phi can be the dark matter candidate?
No, I mean that model, that second model is more economical in terms of symmetries. In both models, the preserved C2 symmetry, that preserved C2 symmetry, apart from guaranteed stability to the dark matter, this guaranteed the radiative nature of the inverse seesaw mechanism. That's why mu parameter is radiatively generated and bar phi doesn't acquire a vacuum expectation value. But the C2 tilde symmetry, this preserved C2 symmetry, arises from the spontaneous breaking of the global lepton number symmetry. But here in that model, we don't need to impose an extra symmetry because by the construction and by the chair assignment, we force that the mu parameter appear at one level. For example, here we don't, the sigma field, we should have even one of the two electrically neutral scalar singlet having even charge on the global lepton number symmetry, they cannot generate a splitting between the real and imaginary part of the bar phi. We cannot build the interaction phi square sigma or phi square sigma rho. We cannot build that kind of interaction because they will not be invariant under the symmetry. So mu parameter.
Remember that the phi should be the real part, and the imaginary part should be the component of the complex scalar, right?
Exactly. The component of yes, this bar phi is a complex scalar, and its real and imaginary part should have different masks in order to close the loop. But here we cannot close the loop. We cannot generate a mu parameter at one loop. We need to generate it at two loop level. And that's why we have these several electrically charged scalar singlet. For example, the C plus minus and the C plus minus in the last two lines of the table of the scalar content, they will mix and they will give rise to H3 4 plus minus, which are the electrically charged scalar. It's a Sibabu topology for that diagram. The other diagram is, the other model is more economical in terms of scalar content. And in that model, in the other model, we had the bar phi square sigma interaction because the sigma scalar field will have a different share on the global lepton number symmetry. And therefore, we could generate mass splitting between the real and imaginary part of the bar phi in the model one. And that's why the mu parameter appear at 1 node level.
Okay. Thank you.
You're welcome. Question from the audience? More questions?
I have an additional question.
Yeah.
A very general question. In the very beginning, you mentioned in one of the first slides that in the 331 model, you can account for the the next one.
What?
Yes, this one. So you can account for the quantization of electric charge. So could you comment very broadly how that works in the 331?
Let me. Maybe I think you should define. Let's say. I mean you can read it for return in the first in the paper that my supervisor, Professor Hoàng Ngọc Long, published in 1994, 13 years ago, and you can get the explain only for the explain of quantization is explained about the numerical and fermion family, because we use the condition of infrared. Let me remember.
Yeah, the number of families has to do with the anomalies, right? Anomaly constellations.
The quantization, I don't remember exactly, but I remember he mentioned in his paper. I can send you the reference later. Yeah.
Yeah, maybe it has to do as well with the anomaly constellation, but it's something that I hear that in the 331 you can explain that, but I never have seen the real vision behind that. So
Yeah, but
it's a curiosity.
I can send you the manuscript because I just use the property of this, and as you said that I didn't rethink about it carefully. So maybe I can send you and we can discuss later.
Yeah, okay, thank you.
So please send me your email or something that I can connect with you.
Okay, I send you.
Yeah, thank you.
I think this has to do for this quantization electric charge could be obtained, for example, yes, Tesio was pointing out, and being combination of the condition for the cancellation of chiral anomalies as well as the definition of the electric charge. Cancellation of chiral anomalies will one the condition that arrive from that will be that the number of fermionic triplet on the residual left has to be equal to the number of fermionic anti-triplet on the residual left. This condition will happen when the number of fermion family has to be a multiplet of 3. On the other hand, we had that the electric chair in this model has to be defined as a T3 plus T. The electric chair operator has to be defined as T3 plus TA plus, T3 plus beta TA plus X, where X corresponds to the U1S chair.
Maybe, sorry, Antonio, maybe it's because we can define the electric shock operator like
yes,
yes,
exactly like this one. And the beta here is -1 divided by square root of 3. Because because here we don't want this value is favored because it will imply, for example, that the third component of the left electronic triplet will be electrically neutral. It will allow for natural implementation of low scale seesaw mechanism just by adding 3 like anti-majorana neutrino. And on the other hand, also this value for the beta will allow to have to avoid exotic electric chair. And then when you take, for example, the quark multiplet with this non-universal U and X chair, then one can, for example, get the electric chair quantization. It seems to be these two conditions, as well as the definition of the electric chair to, for example, to show this quantization of the electric chair. And as been mentioned, more details are provided in this pioneer paper of Professor Long several decades ago. There are more details about that.
Yeah, I think so.
Hmm.
But I will read it carefully because I will read it because that's a nice question for me.
Any more questions, comments? No more questions? Maybe we have one last comment. Yes, this C2 symmetry that is spontaneously broken in model 1 is imposed to forbid, for example, the interaction. In model 1 is to forbid, for example, to forbid the appearance of the mu parameter at 3 level, because if we remove this C2 symmetry, then we had that this like-handed. Maybe you can show the table, please bring the other slides, the table, the particle content, because yes, this C2 symmetry, it was to, because NR, it has lepton numbers, no, the other of the table.
The other table?
Yes. Because here, for example, in that table, you have the right-handed Majorana neutrino to have lepton number chair equal to -1. If we remove this to symmetry, then we could have, for example, yes, and in principle, an R and R bar C there, and with the sigma is yes, and the term with the sigma is forbidden because of the chair. But also we had that field in this model 1, we had this no, this preserved C2 symmetry, we had it to force that the charleton masses should be generated via universal seesaw. Yes, if to avoid to force that the charleton masses be generated by universal seesaw, three-level universal seesaw, and not by the usual Yukawa interaction. Because, for example, if you remove this C2 symmetry, you will have the interaction LF bar, rho, and LR. And we want, for example, that these charleton masses be generated by by the three-level universal seesaw mechanism. That's why we impose this C2 symmetry. And the chair assignment for the sigma, which is 1, it forbids the ter and R bar C at 3 levels. So the mu parameter is radiative generated. Just one comment to mention the purpose of the C2 symmetry. If we remove it, we can still have this mu inverse iso at 1 node level, but then charleton masses, standard model charleton masses, will arise via the Yukawa interaction with the rho scalar triplet, and then we will not have a natural explanation for the smallness of the charleton masses, because in that case, the universal seesaw mechanism will be just an extra contribution, but it will not be the only source for charleton masses. So that's why this two symmetry is imposed to force that the standard model charleton masses be generated via the three-level universal seesaw mechanism mediated by this Charlet vector-like fermion capital E.
Antonio, by universal seesaw, you mean that the charged lepton masses are generated at loop level as well, or not?
No, charleton masses are generated at 3 level.
Level.
Universal seesaw means yes. Taiwan in the topology, the Taiwan seesaw mechanism, but apply for char fermion, and the seesaw messenger will be this capital E.
Ah, I see.
Because if we remove this C2 symmetry, then from that table, we can build the interaction, for example, LF bar, the rho triplet, and LR. that interaction will be invariant under the symmetry because LF bar will have 1/3 on the U1x, LR will be -1, so it will be -2/3, and this -2/3 is cancelled by the chair of the row on the U1x. And similar situation will happen with the chair with the lepton number with the chair under the global lepton number symmetry. So when we assign to the left-handed electronic triplet a non-trivial chair under the broken C2 symmetry, this the C2 symmetry spontaneously broken, then we forbid charge lepton masses via the use of Yukawa interaction, but then we generate them via the mixing with the char vector-like leptons, which behave as a seesaw messenger to implement this three-level universal seesaw mechanism. So here the only radiative mechanism in that model is for the mu parameter.
No, yeah, I see what you mean.
Any question, comment from the audience? If there are no more comments, we send Beam for the very nice and complete seminar, and we meet at the next seminar.
Yeah, thank you. See all of you.
Thank you, Beam.
Thank
And
you.
Merry Christmas, yes, and Happy New Year to all of you.
Happy New Year for all of you. Nice to meet all of you.
Yeah, thank you, Bin, and Merry Christmas to all of you. Bye.
Okay, can
Thank
I
you.
talk with Vinodasa
Bye bye.
Antonio for some
Thank
minutes?
you. Bye bye.
Thank you. Merry Christmas. Bye.
Thank you. Bin, you wanted to say something?
Yeah, I want to say something to you and maybe yeah.
Okay. Yes, we can.
Antonio, so shall I leave or?
Yes,
You want to tell, or you wish?
No. I mean, like, I didn't understand. You Bin had to say something to Antonio, right? Okay, then
I want to say something to talk to Vinuras because I want to have
okay.
a picture of you, and because I want to interview our research group to some of my friends. Maybe I need a picture from you and
Oh, a picture. Yeah, sure.
you know,
Okay.
and
Yeah.
I have project that maybe I don't know whether you can join or not, but I invited Antonio, and so maybe I want to invite you to come to work on axiom data some coupling from between axiom and the boson, like V boson and the prime boson. So for the next meeting, I want to talk with you. It will be on Friday, but